So this will be a little bit different of a class. I did throw in some stuff into this that's going to help benefit specifically for GED math. So we're going to talk about Newton's third law for that. But this is really just general information to talk about really the place in which we live and kind of some of the hazards that are associated with it, because it's really important to understand what's happening in the region in which you live so you know what to prepare for. And so a lot of people don't realize this, and this is actually relatively new science from the past 50 or so years, and we've discovered some pretty incredible potential for earthquakes in the Washington, Oregon, Cascade area. We're talking about some of the most deadly events that could possibly happen in the world in terms of earthquakes. But first, I want to start by talking about what are different types of stresses, what actually causes these events. We're going to talk about how plates interact with each other, how things move in relationship to each other, because this is all of us have experienced events like this, but we don't realize that the events that cause the earthquakes are really catastrophically larger than what we see. So I'm going to talk about kind of some general information about what causes these events. Then we're going to talk about some more stuff that's a little bit, we're going to get a little bit more specific down to what happened in Idaho a couple weeks ago with that earthquake. We're going to start at the whiteboard, and then I'm going to transition to my desktop, and we're going to look at some maps. I'm going to show you some fault lines and some historic earthquake events. Okay, so first up, when we have two interacting pieces of material, let me grab a book real quick. There are really three ways in which plates can interact with each other. Okay, so if I have these books right here, there's three ways in which they can interact physically. I'm talking about physics physically, not physically as in like muscle. They have one option, they can slide back and forth. Okay, this is called a transform fault. Another option is that they can diverge. They can pull apart, just like this. The third option is that they can be pressed together, right? And they can bend upward, one would bend downward, and every now and then they can slip, and one slides on top of the other, okay? Those are really the three different options that plates can move. And so those three different options are going to relate to what we have here. So this first option that we see is commonly what happens in like California. That's the San Andreas Fault, where we have two blocks of crust sliding against each other. Every now and then, they will get stuck in like in a part of that crust. They just get stuck with each other, and then they can't move because they're stuck and they're caught against each other. When enough pressure builds up, they shatter and they break, and that shatter is that release of the stress that's accumulated. Okay. Another option here is movement away. Okay, so that's that diverging. Okay, and what tends to happen in the crust is when you have two plates of crust moving apart from each other, there's a section that lowers. Okay, and that's why we have deserts. That's why we have the Great Salt Plains. That's why we have some lakes. If you travel to Nevada or even into southern Idaho, you're going to see things that look kind of like this, where you have low-lying valleys and really tall, high cliffs. That's really common to see all over the world. It's pretty shocking scenery. And the third option is when you have that crust moving against each other, moving towards each other, okay? And this is what tends to happen here. If you have two plates of crust moving against each other, you're going to have a section that gets uplifted, okay? Causing things like mountains, okay? So all three of these different types of movements have earthquake intensity associated with them. So first up, a lot of people hear about the San Andreas Fault, right? And how scary and deadly that can be, and how, oh, we're going to have that big one, and eventually California is going to fall off into the ocean. Okay? You hear that sometimes. But really, right here, your earthquake potential max is about a 7.0. Okay? And that's a pretty big earthquake. Typically, you're not going to get too much more than this. There's a few rare cases where you can, but in general, That's about the max that you're going to expect for a strike slip or a transform fault. When we have crust moving apart, where we have that crust that's kind of stretching apart, sliding, it'll get stuck, then it'll break apart. Your earthquake potential here is somewhere in the realm of like a max 5.5, something like that. Now, when we get to down here, which is the biggest one, you have a max potential of really in the realm of like a 9.0 or even greater in some cases. Now I use these 7.0, 5.5, 9.0. I'm sure a lot of you have seen those before, but one thing I want to make note of real quick is this is the Richter scale, and it goes from 1.0 to 10.0. 10 is the max on the Richter scale, okay? Now, what's interesting here is if I go from a 1.0 earthquake to a 2.0 earthquake, what that really means is that the energy that's being released by that quake is 10 times greater. So anytime you increase from a 1 to a 2 or from a 2 to a 3, you're increasing the energy that's being released, the stored up energy, by 10 times. So because each one is 10 times, right? If I go from a 1.0 to a 3.0, it's not 20 times that the energy is being released, it's 10 times 10, which means 100 times the energy release, okay? So if I were to go from a 1.0 to, say, a 5.0, that's a lot of energy to be released. That's a 10 times 10 times 10 times 10 times 10. That's a huge amount of energy. So when we think about this 7.0, right, which we know are big earthquakes that can cause a lot of damage, which is what happens in California, think about these 9.0s. This is 100 times greater of an earthquake than the 7.0. And this right here is what we have on our coastline, okay? Now let me explain why that is. Because there's a lot of this stress that we've just discussed, but let's talk about the reason why we have this crazy potential here in Washington, Idaho, Oregon. So let me erase this and I'll draw another quick picture for us to talk about.
Hey, Alex.
Did I hear a voice? Did somebody have a question?
Yes, me, Danny.
Go ahead, Danny.
That last freaking earthquake that was supposedly in Idaho, I heard it was actually from like around Yellowstone. Is that true?
No.
No?
No, I'll get into that soon, okay? Let me get like this background knowledge then, and then we're target specifically what happened in Idaho and why that was kind of, I wouldn't say it's special or unique, but it's cool, okay?
Okay.
So, but everything that I'm talking about now is really the reason for that earthquake that happened in Idaho, okay? So, what we have on our coastline, there's two different types of crust, okay? There is oceanic crust, which is obviously underneath the ocean, which is very thin, okay? So this is ocean crust, right? And then we have what it's butting up against is the continental crust. So the continental crust is going to look something like this. The continental crust is much denser. It is much thicker, and it's way less dense. So it's pretty buoyant. It wants to stay up top. Where oceanic crust is much denser, it's much heavier. So it tends, when these two things interact and they start converging, the denser, the heavier piece of crust is going to be pushed underneath the lighter crust, the less dense crust, which is continental crust. I'm going to change how I drew this just a little bit. Okay, so what we have here, we're going to talk about, let's say this is Seattle. This is Eberg, Ellensburg, and let's say us right here, this is all Washington, this is going to be Spokane. Okay, so does that make sense what I drew? This is the continental crust in which we live. This is the oceanic crust subducting underneath our continental crust. These are the kind of three main areas, kind of the middle of the state, right near the ocean, and then kind of further in near Idaho. Okay, so we have this oceanic crust butting into the continental crust. And what happens is as it's subducting under, as it's grinding and sliding underneath, eventually it'll get stuck. It'll get caught, right? Because rock is going to lock against itself. And when it locks like this, it's going to slowly build up pressure, and it's going to start to buckle. The crust is going to start to buckle. It's going to start out flat, and as that pressure builds, you're going to get higher and higher as that pressure builds until you reach a breaking point, okay? When this stuck part can no longer stay stuck, and it fractures, releasing that energy, okay? And when it releases that energy, when it releases that stress, it causes an earthquake, okay? I'm gonna put the ocean right here, okay? Now, why is that a huge deal? Well, this is a plate boundary, okay? This is where continental plates are interacting. This is where a lot of energy can be built up. And this is where I want to talk about Newton's third law, okay? Okay? Some of you might know what the third law is, but if you don't, I'm going to put it down into very generalized terms. Newton's law is essentially called the normal force, okay? Essentially what it's saying is if I say I'm a boxer and I punch somebody, right? I'm going to punch them. I'm going to transfer the energy within my body into that person. And that person, because if I punch them, I'm going to feel a feedback. My hand's going to stop. I'm going to feel a feedback from their body, right? That feedback is the normal force. That is Newton's third law, okay? So if I were to, let's say I'll punch a wall now. It hurts to punch a wall or it hurts to punch a piece of concrete because however much force I put into that punch, I'm going to get back in return, okay? That if I punch a block, that block's going to punch me right back, and that's why it hurts to punch a block of concrete or something. It's also the reason why, so this is me, okay? And I have gravity acting on my body to hold me down on the earth, right? But because this force is being applied to my body into the ground, what has to happen so I don't sink? If there's no other force applying onto my body, then I would just start to sink, right? But I don't, and obviously that doesn't sound right for us because we've lived on this earth our whole lives. Generation, you haven't heard of people just suddenly sinking into the floor. The reason we don't is because the earth feels this force and they apply a force of the exact same amount back onto your body. So it balances that force out. That's why we're able to stand. That's why, that's the normal force. That's why we're able to run. That's why we're able to walk. That's why we're able to hug somebody. It's the normal force. So that's in small terms, but the same concept is happening in these large areas when we have interacting crusts, okay? So I mentioned this was a very dense piece of crust. This was a very much less dense piece of crust. It's really interesting to think about because you can actually, even though we have that normal force, which is trying to balance things out, it's trying to balance out the world, sometimes you can overwhelm that force. So think about like a black belt karate master or something. When they hit that piece of wood, when they karate chop through that piece of wood, they break that piece of wood because the force that they're applying to that object overwhelms that object, okay? And the response to that stress, the stress of chopping that piece of wood, is the shatter, okay? The same thing happens with crust. So because crust comes in all different shapes and sizes and densities, I have two pieces of crust right here. They're about the same size, right? This right here, this piece of crust is light enough to float in water, whereas this piece of crust, it weighs almost 20 pounds. So what do you think is going to happen when I have that crust that's very light, very dense, interacting with that very dense, thin crust? One of them is going to shatter. One of them is going to eventually overwhelm the other, like that karate master chopping through that block of wood. So with that, let me think. Okay, I want to talk about one more thing. as this stress is applied, remember, these are moving towards each other. This is moving against each other relative, okay? Now, there's something called the accordion effect that geologists are able to measure. And so if you think about an accordion, when I'm pulling that accordion, if I hold one part firm, the furthest part away from the accordion is going to move the most. Whereas if I'm looking at a part that's close to this side, it's not going to move as much as the other handle, right? The same thing is going to happen to this crust. As the stress is applying, Seattle is going to move with this motion. So this crust is going to buckle upward and move this way because it's not strong enough to hold this stress. Okay, so Seattle is actually moving in that kind of direction. Okay, that's an arrow. And we actually see that every year Seattle moves from its previous spot in the previous year somewhere between 6 to 10 centimeters a year. Okay, now in Ellensburg, we also measure the movement that Ellensburg is doing, and that's like 2 to 3 centimeters. We also see it in Spokane and Idaho. The movement there is much less. We're talking maybe a few millimeters to a centimeter. So we're seeing this movement. So like 6 to 10 centimeters. You can see the closer to the interaction of the plates, you're going to have more movement. And as you get further and further away, you're still having movement, but it's a little bit less and less intense. That's why in the center of our continent, we're talking about the Midwest, we don't have very many earthquakes. We don't have a lot of movement going on there because there's no interacting plates in the middle of the continent. Now, this is massive interaction, okay? But this force is being transferred to the crust, and eventually there's spots on the crust that start to crack and shatter. And it'll start to break. It'll start to crack at the surface because it's trying to absorb that force, as much of that force as it possibly can. And when it starts to crack and shatter like this, those are faults. Those are called microfaults. So you have these major interactions between the continental boundaries, which are huge faults, and they cause these smaller microfaults. Okay, does that make sense to everybody so far? Before we go to the computer and I show you some stuff.
Yeah.
Okay.
Yes, sir.
So what I'm going to do, I'm going to stop my video for just a second, move over to the computer, and we're going to look at some interesting things. Okay, so I got my video set up. I'm going to share my screen so you guys can see what I'm looking at.
Barack Obama.
Let me know when you guys can see that.
Can see it.
I can see it.
Okay. So remember how I talked about those continental plates, okay? Which is the sections of the Earth that are colliding against each other. So what I'm going to show on here, it's going to be a little bit difficult to see right away. Oh, come on. Let me move something out of the way real quick. In these red lines, these red lines are going to show those plates, okay? Does everybody see those red lines that popped up? You might need to zoom in a little bit if you can.
Oh, we can. Dope. Yeah, I see him.
Okay, so you see where my mouse is. It's tracing the continental plate all the way up and around, okay? So based on what I was just telling you guys, we would expect that along these red lines where those plates are interacting with one another, that these are the places where the vast majority of all earthquakes on the planet occur. So over here we have Japan. Please make a note of Japan on this side. Remember what it looks like right now, because what I'm going to do next is actually post historic earthquakes, okay? So let's look at what happens. Take that in for a sec.
There's a lot over there.
Okay.
Holy crap, Japan has been flooded with earthquakes.
But take a look in general.
Cause the shape of the continents.
Say that one more time. I didn't quite understand you. Sorry, I didn't get that. I'm just going to keep on going. If you have that question, we can talk about it again after.
Dang.
So make a note of, look, these major earthquakes are following those continental lines where those plates are interacting all the way around. This is how we knew where the plates were before we were able to use like satellites and LiDAR data to actually track them and see them. It's because of this that we knew, because we could track, okay, where are these earthquakes happening? All right, this must be where the plate boundaries are.
Hey, Alex.
No, we did a pretty good job of that. What's up?
Why is there so many in like what is that area?
Are you talking about up here?
Yeah.
Okay, I'll talk about that real quick. Does anybody know what part of the world this is?
Eurasia?
So right here we got China. We got China right here. We got India right here.
Oh, okay.
Anybody know where Mount Everest is?
Nah, I only know where the United States.
It's right over here. Okay. So what's happened is India, and this is just a quick side note for you guys since you asked that question. India actually belongs all the way down here. This is where it broke off. India broke off of South Africa. And it just shot all the way north. And this is a separate plate because you can see these red lines. It's part of a different plate than Eurasia up here. So this has shot up and it has crashed into Eurasia really fast, really hard, causing that crust to uplift really strongly. And because that's happening so quickly, that crust is moving so much from India crashing into the continent, it has caused a ton of earthquakes, massive earthquake events in that area.
Damn.
And that's why we have the Himalayas there, which are the tallest mountains in the world. It's because of that interaction, that crash that's happened.
Damn, okay.
Geologically speaking, like it was moving at freaking like billion-dollar sports car speeds compared to the rest of the plates. So I want you guys to look at something real quick because we're going to zoom in on this next. What do you notice over here? This is where Washington is, in this spot where my mouse is. There's something weird that's happened. Look, we have this red line where the plates are interacting happening, and there's all earthquakes down here, but all of a sudden, there's a gap. There's a gap. We still see that red line, but there's a gap of earthquakes right in here. Okay? I'm going to zoom in on that next. Let me know when you can see this next screen.
Yeah, we can see it.
So this is a zoomed in section of that. So because we have satellite data now, take a look at where my mouse is. What does this all look like? This is something weird happening, huh?
Yeah.
Like, why do we have such sharp angles here in nature? You don't usually see sharp, like perfectly square, almost perfectly 90 degrees angles happening in nature.
Pretty sure that's where shit's breaking, right?
That is where the fault lines are. So let me bring up the tectonic plates. So that red line is going to show up in just a moment. So we can see that red line coming in, and it's following that almost exactly. What's up, Billy? Was that you?
You know, this whole time I've been wanting to ask you if this was going to be about tectonic plates, but I didn't want to sound stupid, so I just kept my mouth shut.
You got to work on that, man. You're a smart guy. Okay, so now let me bring up those earthquakes again. So we can see down here, we have all those earthquakes, okay? And then we have a gap in this section. And then we have those earthquakes again up here. This is a very unique situation that we have in our part of the world, in our state. Okay, I just took those earthquakes off real quick because I want you to look at something. I zoomed out just a little bit. We have this right here, this fault line coming in from California, right? Where it's just one fault line, okay? And that's the San Andreas, which is all down here. And then that fault line, it breaks off into two all of a sudden. One goes west, the other one starts heading north. And then we have this little section of a plate. Because remember, those red lines are signifying separate, broken apart plates, right? And so we have this weird broken up plate right here. So this side right here of the plate is subducting underneath the continent. And then the same thing is happening here. So it's building up a lot and lot of stress. And the reason we haven't had a lot of earthquakes in this spot right now, let me bring that up again. The reason we haven't had a ton of earthquakes here or here is because it is in a zone of when it is just building up more and more stress over time. And plates can build up stress for hundreds of years. They can build up stress for thousands of years. Humans haven't been in this part of the world very long. We, as geologists, we can look at the rock record and we actually know the last time we had a major earthquake in this spot. And that was, we actually have it down to the morning and the specific time of day, the exact date. We know when it happened using geologic records as well as Native American storytelling and the records that they've kept. So we know when it happened. I don't remember exactly what it is now. I'm not prepared on that. I just don't remember. But that was about 200 years ago before we migrated to this part of the world, and the only people that were here were Native Americans. So that's why we don't have record of it, because it was before that. It was before we colonized this part of the world. So because we have this stress building up, it's building up really strongly here, but over in Idaho, it's also building up that stress. That stress is building up all through the state into Idaho. Okay? Let me see if there's anything else I want to show you on this. There is something else I want to show you on this. So I mentioned that you have these major faults, which are the continental divides, and then you have those micro faults, okay? Those smaller faults that are a consequence of that major interaction. It's the crust breaking apart. So I'm going to show that next. I'm going to turn off the earthquakes just so you can see these faults a little bit better. And I'm going to zoom in to this one. You can see all those red lines that showed up. I'm actually going to change something so you can see them a little bit better. Okay, so we see all these red lines. This is where stress is building up, and this is where microfractures have happened. This is where little earthquakes has happened. So if you look here in Idaho, take a look at all these faults. And by the way, I don't know if you guys have ever thought about this, but there is a reason why all of these faults are going pretty much north-south. And it's for the same reason that pretty much all mountain ranges in the US also run about north-south. That's no coincidence. So we see all these faults here, right? So now let's get to the part where we talk about what happened in, okay? So I'm gonna bring up the epicenter of that earthquake. See that little star that popped up? That is the epicenter of where that earthquake happened, that 6.5 that we had a couple weeks ago. Now, you can see it's pretty close to all of these faults, these red ones. But what might blow some of your minds to know is these red lines, this is less, all of these red lines together that we have tracked is less than 1% of the total faults that we have mapped. The red lines that this website is only keeping track of are ones that have shown consistent movement over like the past 10 years, okay? So we have a lot of
So
area
it's not
around
showing
it.
none of the other ones?
It's only showing less than 1%. Most of them are really small. Like this is spanning cities, right?
Yeah.
Like even in Spokane, Spokane's right over here. Spokane has a fault running right through downtown Spokane. But it's not showing that because it's not a fault that moves very much. So
Oh,
it's,
fuck,
they're not going to
really?
use geologic manpower.
Oh, that's why we
track
don't know about that one too much. The one
And
you
that's
were
why
talking
we're not-
about
that's why
yesterday.
that's why most people don't really talk about that fault. It has shown history of like a 5.0 earthquake in the past, but the recurrence interval, the amount of time it takes for that fault to build up enough stress to release an earthquake like that takes a very long time. We're talking hundreds of years.
Yeah.
So eventually, yes, it is going to go off the fault for Spokane, and once that goes off, guess what? That fault's going to appear on this map.
It's going to
But
be
until
kind of
then-
like Mount St. Helens, like the volcano.
Not quite to that extent. Not quite. The issue Spokane has right now is because for a long time before we even built Spokane, we didn't realize the potential for earthquakes in this part of the region. So we didn't build buildings in preparation for that. So they're not built to withstand earthquakes. Whereas if you look at places like Japan, all of their economy, all of their infrastructure, all of their engineering of their buildings, they engineer their buildings specifically to withstand major shaking events. That's why they don't have like whole cities collapse. Whereas if you look in Spokane, we have quite a few brick buildings in Spokane, right? When
Yeah.
you start shaking brick buildings, they just tumble and they crumble, right? They just fall apart. It doesn't take a whole lot of intense shaking for that to happen. So the issue Spokane is going to have is that we're not engineered for these events right
So
now
what you
because we don't
saying-
have them very often.
So what you're saying that if like we get hit by like a 9.0, Spokane's gone.
Yeah.
Spokane,
kinda.
so, okay, let me tell you this. We can get upwards of 9.0 on this side of the state, right?
Yeah.
That 9.0, we're not going to feel it over here, okay? We had that 6.0 down here in Idaho. Up here in Spokane, it barely even registered. It registered as like a 0.4 or something.
Alex,
So,
so you're saying like hundreds of years from now, downtown will have an earthquake?
Spokane?
Yeah, downtown.
Yeah, so it's going to have another earthquake.
Okay,
We don't
so-
know exactly when. A
Yeah,
recurrence interval, which is how we track these events, is just an average, okay? So we can
Okay.
track multiple events, and we look at the time it takes between those events to occur. So we have one, we see how long it takes for the next one to occur. Then we look at that one that just occurred, and we see how long it takes for the next one to occur. And we can see these earthquakes in the rock, okay? When these earthquakes happen, we see shattered rock, and we can track, okay, we can date some stuff in that rock so we know exactly how long it took between these events. And what's kind of crazy is, I don't know the details of the Spokane fault myself, but I believe the recurrence interval, the average time it takes for these earthquakes to happen is somewhere around 300 years, okay? I have studied the West Coast quite a bit. The recurrence interval there is somewhere in the realm of 220 to 500 years for the recurrence interval. We don't know exactly because we haven't been able to see a ton of events to get really locked down what an average event looks like or what an average time it takes for that to happen looks like. Now, but we can see a lot of events, and between events, because we don't have enough data points, between events we see that you can have anywhere from 1,000 years between events to as little as 50 years between events. Okay, so it's really hard to determine that. Does that make sense? I'm not trying to scare you guys, absolutely not. This is just something that we need to be aware of, that this can happen,
Yeah.
because when we have that major event on the west side, where are the people going to go? They're going to go where it's safe. They're going to move inland away from the coastline, right? So we need to be prepared to support those people who, guess what? Spokane is one of the biggest cities in Washington. We're going to have a lot of influx of people coming in, because even though we can have major earthquake events here, we're not going to feel it very much in Spokane, right? So our job is to be prepared for that, to support those people when that event happens, if it happens in our lifetime. The other thing to also be aware of is, on the west side, it's really not the earthquake that is our major concern. Yeah, we're going to have some shaking. Yeah, earthquakes are not fun. But on the west side, the concern is more tsunami potential. It's the tsunamis that would kill a lot more people if we don't prepare for it. And thankfully, the science for like predicting these earthquakes and predicting like tsunami extent has gotten so freaking good, thanks to a lot of work by geologists all over the world. So we actually have pretty much developed a system where we know we can give like a 2 to 5 minute window to people to let them know this is when the earthquake's going to happen. And that 2 to 5 minutes gives you plenty of time to get to a safe space, to brace yourself and prepare for that earthquake to happen. And then once that earthquake happens, guess what? You just start moving inland if you live on the west side, so you get away from the tsunami. Okay? So science has prepared us, science is protecting us, and that's our job as geologists, is to help people live through events like this. Even though we have this great potential, we have a lot of really brilliant minds working on these things to help protect all of us. And our job as citizens is to really be aware of the science, be aware of the potential. And when our scientists warn us about these events, listen to them, because they're not doing it for fun. They're doing it because they care, and they've dedicated their lives to these things. So we got a little bit off topic on that. Let me show you guys one more thing before we end.
Alex. Hey, you remember when those tsunamis hit and like hurricane? Well, those were hurricanes, weren't they? A couple years ago, and they fucked up.
Yeah, we have tsunamis and hurricanes all over the world all year.
Yeah, but we seen those coming.
Yeah, and we can track those.
Yeah, so pretty tight.
Now we can see hurricanes a little bit better than earthquakes, for sure, because we can just, look at our satellite images and track the eye of the storm.
Yeah.
Whereas we can't see underneath the earth as well. We actually can see quite a bit. We know exactly what this broken piece of crust is doing underneath, and why it's giving us such unique, really catastrophic potential. And I use like these words for catastrophic. These are actually scientific words. I know in like media they use them as like scare tactic words. I'm not using it that way. I'm not using these words to scare you guys. These are scientific words in geology. Catastrophic means major potential.
Well, when that does happen, it won't be in our lifetime. So
we don't know. That's the thing. We don't know.
Yeah.
Remember, I said we've tracked these events. Sometimes between events is 1,000 years. Sometimes it's between 50 years. We don't know which it is, right? We could have that event on the west side happen right now, right? We could also have it happen in 1,000 years from now. Now we're tracking that and we're watching this because there are signs that we look for as scientists to know if something big is about to happen, but we can't predict when we're going to get those signs. Okay. So take a look at this map. What this is showing is basically all the earthquakes that have happened since midnight. Okay. That on this map here, it's showing 87 earthquakes that have happened since midnight. Okay, and that's quite a bit. We have a lot of movement that is always happening in the crust. But do you see anything kind of unique that's happening in Idaho, maybe? Take a look right here. What do you see there?
A lot of earthquakes.
There's a lot of earthquakes. And this is just the past day, right? I just zoomed into Idaho, okay? Now, why don't I go the past week?
It's about to blow up.
But all of a sudden, I get a warning on my computer that says, are you sure you want to do this? Because this might slow down your computer. Look at how many more showed up in just the past week, okay? Now I'm going to eliminate some of those, just the really small ones. I'm going to go the past month. So I took away all the small ones under 2.5 magnitude. And this is all the earthquakes that have happened there in the past month. And what do you think this big one is right here, this big circle? The bigger the circle means the bigger the quake. Do you think that's our 6.5? I think it is.
Yep.
So, what is unique about this spot in Idaho right now that I've been tracking the past couple of weeks is that there's a zipper effect that tends to happen with earthquakes along fault lines, okay? And what I mean by that is when we have one major event occur on the fault line, it's just one part of the fault line that is slipped, it means that when we have release pressure in one area, so that earthquake occurs, the areas around it start to gain pressure, and they tend to gain pressure so quickly that it overwhelms that normal force that we were talking about a few minutes ago, causing more fractures. And the way that we release this gained energy is in the form of earthquakes. That's why when we look at this map, we have a ton of earthquakes that have happened in just around this 6.5. And by looking at the number of earthquakes that we see here, you can kind of see kind of how the fault's running. It's running in a north-southish direction, right?
Yeah.
So this is going to continue to happen
for the next couple months. We're going to see a lot of little micro earthquakes in this area. They're not going to get above like a 3.0. Okay, these are very small. Most of them are going to be in the 1.0 range. So like rocking your baby to sleep is what it's going to feel like at most. But that's what happens. We have this major earthquake, and then we have sometimes hundreds and thousands of smaller micro earthquakes that occur after these events. So think about that when I was talking about that 9.0 potential earthquake on the west side that we need to be aware of and prepare for, because people are going to want to leave those areas, right? And we need to embrace that. So the last thing I want to leave you guys with is, well, one, actually, let me go, hold on. I didn't tell you the name of this. Okay, I don't know what happened. So the name of this broken crust that we have, it would be good for all of you to know its name because it comes up in the news every now and then. It is called the Juan de Fuca plate. Juan de Fuca. Okay, so just be aware of that name because it's important to know about this thing. The other thing that I want to leave you with is
What's the name?
I glossed over a lot of really complicated topics. So one of the things I want to leave you with is I mentioned that there's just a motion going from east to west for that convergence. Okay, nature is not so simple. Okay, what is actually happening is this Juan de Fuca plate is actually rotating. It's not just evenly subducting underneath the continental crust. It is rotating where the top part is subducting faster, where this lower section is actually moving towards the west a little bit. So there's spreading at the bottom and there's convergence at the top. It's rotating clockwise, okay? And that has caused the crust up here to really do essentially the same thing. So we have like Washington, northern Idaho, and to about where that earthquake happened, converging. And then the lower sections, there's a divergence that is happening in response to that. So there's a spreading of the crust and a convergence of the crust. The other last thing I want to mention is I showed you those 3 different pictures of the faults, how they can slide against each other, they can come together, or they can pull apart. Well, in nature, there is no such thing as any of those faults. What I mean by that is there's no such thing as a perfectly sliding fault. There's no such thing as a perfectly converging fault. There is only one type of fault that we see in nature because nature is a complicated bastard, I'm just going to say. They're not so simple. The one type of fault that we see is called an oblique fault. And what oblique means is that you have any combination of those 2 movements happening. You have sliding diagonally, which means that you have some strike slip happening and you have some subduction happening. You have some convergence, some pulling apart. And that's kind of weird to think about when I say that, because yes, in fact, in the same parts of the crust, you can have both divergence, which is the pulling apart of the crust, and at the same time, convergence, where the crust is pushing against itself. It seems counterintuitive, and that's because nature frickin' sucks. And it's complicated. So that's just the last thought I want to leave you guys with. And that's all I have for you. I hope you guys found that kind of interesting and educational and maybe a little bit enlightening, and hopefully you want to be geologists.
Yes.
Wow, thanks, Alex.
Yeah, I took some notes.
If you guys have any questions about that, you can ask me now or shoot me a message later.
What was that
For
name
sure.
you said, remember? The Oka what?
Juan de Fuca, Juan space DE space FUCA. Juan de Fuca.
Fuca. Yeah. All right.
Okay. Talk to you guys soon.
All righty, Alex.
Bye.
I took some notes.
All right, see
Appreciate
you
it.
later, Alex.